All right, so guys, starting again and again, I know we're off to sort of a slow reconnecting step. So guys, what we're looking at here are mass problems. So the name comes from the process. You're always starting with a mass, you're always setting your goal at a mass, and then guys, based upon the essentials that you needed to know from the previous unit, all you've got to do is convert grams to moles, and then we get the mole-to-mole ratio that we call the stoichiometric ratio from the balanced equation. And then, guys, we convert moles back out to grams. It's always the same 3 steps. So if you let your eye scan down these, the only thing that makes it different is maybe you have to write your balanced equation, which is there where you get the ratio from. But, guys, they're always the same 3 steps. Go ahead, McKay. Yeah, that's a really good question. So how do you know what your starting point and your goal is? And I want to talk with you about it because the rules are going to change today. This is the only new thing, well, one of the 2 new things you're going to learn today. So looking at the homework assignment itself, for example, if you read number 1, it says glucose is used as a source of energy, the overall reaction is. And then it says calculate the number of grams of oxygen. So that immediately tells us our goal that we're solving for grams of oxygen. So now we need our starting point. And it says calculate the number of grams of oxygen needed to oxidize 12.5 grams of glucose. So the number becomes our starting point. We start with 12.5 grams of glucose, we set our goal at oxygen, and then the process is the same every single time. So what you're going to find today in class is the only difference is going to be instead of your starting point being the only number you're given, you're going to be given 2 numbers, and you're going to have to figure out which one to start with, and we'll talk about that in just a minute. So guys, what else? Other things that you need clarification on before you can then honestly go in tonight and say, yes, this is done, and I got my questions answered. Yeah?
Just remember one sentence, oxygen.
Yeah. Great question. And so, so when we talk about oxygen, when it's by itself. So oxygen by itself is O2 because it's diatomic. And then remember, because we're starting to move up on the test, right? So iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen are the diatomics. And so those are the ones that you'll never see by themselves. Either they're bonded to something else or they bond in packages of 2. Yep. What else, you guys? You really okay? You're sure? Okay. So guys, do this. Slide your homework to the side. Do not put it away. You will have time to work on your homework today. And then guys, you're going to need, really just note-taking materials. I'll do the math for you. So just grab something you can take notes with. Grab something you can take notes on. We're going to dig in, and very quickly, you're going to be working on homework. All right, so this goes away. McKay on his daily pencil sharpening trip. So guys, again, make note to yourself to record this homework assignment before midnight tonight. I know you're out of practice on that. Don't forget. And so guys, what I want to do is I want to gather around the calendar with you for a couple minutes. Remind you that Orem High School is an absolute disaster in the spring. Spring break, it just gets worse. So guys, please do your part. Stay caught up with the calendar. Make sure that you know what's going on. When you know things will be keeping you out of class, all you got to do is talk with me ahead of time. We can accommodate anything that we know about in advance. So guys, let me explain to you the way the rest of this unit and then the rest of the year goes. So guys, today is the last of the new material for the unit. You'll notice that percent yield is not only a topic today, it's also the lab that we're going to be doing on Thursday. Then guys, next Monday, test over this unit, which will be the first to last test of the year. Then guys, after that, the rest of the year is all about getting you into lab. So the next unit starts, we're in lab. Then we wrap up that lab, then we've got a day of new material, and then guys, you're right back in lab. Then new material, then right back in lab, and then this is actually a lab. So guys, with the end of the year coming, things are active, you're up, you're in lab a lot. And then guys, we'll have one more unit test. You will not take a comprehensive final in this class. We decided that given the craziness of the school year that we're not going to give a comprehensive final. We decided against that. Normally we do. This year we're not going to. So we will end on the 20th with a unit test. We don't yet know what the end of school looks like those last couple days in May, but we'll be done with school stuff on the 20th. The only thing you need to know, though, guys, is you will not be able to do remediation for this last unit simply because we won't have time to do it. So on this last unit, your score on that test stands, and there's nothing you can do to change it. So there's really nothing else to do because it's so close to the end of the year. So, guys, questions about the calendar? You guys okay? All right. So again, guys, as things come up, as your lives get crazy, please make sure you're communicating. And you're going to find me very, very flexible. Just make sure you're doing your part. All right. So we're going to get rid of this. We're going to grab a hold of this. And guys, this is how we're going to wrap up the unit and how we are going to prepare for the lab that we're doing next time. So guys, the date today is what? The 14th is today? Today's the 12th. Oh, the 12th. So guys, the date today is the 12th, and these are the two things that we're doing today. And we're going to chip these away one at a time, and when we're done, and you'll have time to work on some homework. So guys, today what we're going to do is we're going to address two completely unrelated concepts. So the first thing we're going to do is talk about an idea called percent yield. It kind of sounds like percent error. You're going to find out that it's the opposite of percent error. Then guys, to wrap up the day, we're going to talk about limiting reactants, and when we're done, and that'll be the end of the day. So guys, getting into this, please understand that this and is a hard and. These are not related to each other. So we're going to do one, and then we're going to stop, and then we're going to do the other, and then we're going to go on from there. So you guys ready to go? Here we go. All right. So guys, percent yield first. Don't write down this first page of slides, but let's put this in context. So here's where we are. So guys, what we've been saying for this entire unit is that when we look at balanced equations, we've got reactants that are turning into products. Well, today what we're going to do is we're going to talk about the answer to two questions. So guys, question number one is this. How much product should a reaction create? And guys, the answer to that is percent yield. So again, how much product should a reaction create? And the answer is percent yield. Then the second question that we're going to ask is when will a reaction stop? And the answer to that is limiting reactant. So guys, these two concepts actually answer these two questions. How much product should you get, and when do reactions quit? So guys, let's get started by looking at question number one, and that's percent yield. I would encourage you to write down the definition. This is worth scratching down. So guys, percent yield is a ratio. It is a ratio that compares the amount of product that is produced with the amount that should be produced. So the way that I said it originally is it's a ratio comparing the actual amount of product with the amount that should be produced. But guys, because it's a ratio, you're probably picking up on the idea that mathematically ratios are fractions. And so this is actually the percent yield equation written out in mathematical form. Now, guys, as is always the case, you will never memorize equations in this class. They'll always be given to you on the test. So all you got to do is figure out how to plug in the numbers. But guys, in order to do that, you need to know what the numbers are. So let me give you the definitions. So guys, the actual yield comes from experimentation. Today, I'll give you the numbers. On Thursday, you're going to measure them in lab. But guys, the actual yield is the amount that you actually made. That's where the name comes from. And that actually comes from collected data, or I'll tell you. But then, guys, the theoretical yield is predicted by a mass-mass problem. And this is the tie back to the homework that we just looked at. So, guys, mass-mass calculations become the way that we know the theoretical yield. If you really understand mass-mass problems, maybe that makes sense in your head. If not, I'll show you, and I think it'll make more sense in a minute. You guys all caught up? All right. It is the first day after spring break. And we instituted the yearly spring break ritual, shaving off the beard. Ah, felt so good. Like, remember how hot it was last Saturday? I was so grumpy. I was like, oh my gosh, I was like burning up doing housework. And yeah, every spring break I shave off my beard and then I grow it every Thanksgiving, except for in COVID. And I was just so lazy in COVID that I didn't shave it off last year. But it had to go. It was trouble. All right, you guys caught up now? Okay, so guys, let me then do this, because McKay, this is going to get to the thing that you didn't even know you were asking. But earlier you said, how do we know what we're solving for? How do we know where to start, right? Well, guys, in these problems, that gets a little bit tricky. So let me give you the steps for solving these, and this will bring some clarity. So it used to be when we solved mass-mass problems, your starting point was the only number that you were given. The problem here is that you're going to be given two numbers. So guys, let me explain to you how to make sense of this. So step number one in solving mass-mass problems is to write a balanced equation. That makes sense because we need that in order to have the stoichiometric ratio for the mass-mass problem. Then guys, after that, step number two is start with the mass of a reactant. That's the trick. Your starting point will always be the mass of a reactant. Then what about your goal? Well, your goal will then be the mass of what we call the known product. It's the product that we know the mass of. So guys, this is the only little twist from the mass-mass problems that we were solving before, is that our starting point is always the mass of a reactant, and our goal is always the mass of a known product. Then guys, from there, step 4, solve the mass-mass problem, and then finally step 5, use the result of that as the theoretical yield in your percent yield equation. And guys, by the way, this is exactly what you're going to be doing in lab on Thursday. You're going to go into lab, you're going to gather the mass of your reactant, you're going to weigh it out, then you're going to do the reaction, collect your product, and then you're going to use that and a mass-mass calculation to figure out your percent yield. So as you're practicing, as you're learning this, as you're doing homework, really what you're doing is lab prep, because it's exactly what you're doing in lab. So guys, what we're going to do, if you're okay with this, is I'm going to show you an example of this. Then we're going to make sure you're really good on these ideas of percent yield. If you're good, we're going to do really quickly a little thing with limiting reactants, and then you're going to have a good amount of time to get your homework done. You guys ready to go? Okay, so let me show you an example. I don't know that you need to write down the question, but just read it with me, and then let's solve it together. So guys, it says this. You take 15.5 grams of methane, that's Bunsen burner gas, and you combine it, you light it on fire, and you let it burn with excess oxygen. And guys, excess just means all you need. So we take 15.5 grams of Bunsen burner gas, light it on fire with all the oxygen we need, and then imagine that we collect the water that's created, and we get 32.1 grams of water. How did we do? Did we lose a bunch of water and we should have collected a lot more? Or is that pretty good? Is 32.1 grams about all of the water that we should have collected? And guys, that's what percent yield is all about. How did you do? Of all the product you could have collected, how did you do? So in order to do this, we need to do this percent yield process. So guys, step number 1, combustion reaction. I would strongly encourage you to write this down. Remember too, guys, the test is next Monday, right? So refamiliarize yourself with these reaction types, single, double displacement, decomposition, synthesis, and then combustion. Remember, combustion is always a hydrocarbon reacting with oxygen to produce carbon dioxide and water. So now, guys, watch. Problem-solving strategy that will make your life a whole lot easier. Once you've got the balanced equation written down, guys, what I'd really encourage you to do then is find the masses in the problem and write them down underneath the things in the balanced equation. So 15.5 grams of CH4, write it down underneath the CH4. You probably don't need to write the CH4 again, but you'll see in a minute why I did. Some of you probably see where this is headed. Animations. Then, guys, the other one that we need is the 32.1 grams of water. So I'm going to write that down over here. So, guys, fundamentally, then the question is this. 15.5 grams of Bunsen burner gas, all the oxygen that we need. We collect 32.1 grams of water. How'd we do? That's the question we're answering. So to do this, step 1, balanced equation. Step 2 is what? Where do we start? With the mass of the reactant. That's the one on the left. So guys, what we're going to do is we are then going to draw out our dimensional analysis line. And now you ready? This took me a really long time, so you got to watch. So guys, we are going to start with the mass of the reactant. And it will always be the mass of a reactant. Now, guys, step number 3. It says set your goal at the mass of the known product. Well, guys, we don't know anything about the carbon dioxide, but we do know the mass of the water, so that's going to be our goal, grams of water. Now, guys, at this point, it's just a mass-mass problem, right? And you told me when we were grading homework that you understood mass-mass problems. Kyle asked the question about oxygen and other diatomics. McKay asked the question about how do we know where to start and where we're going, which we just established. But, guys, none of you asked questions about the process of mass-mass problems, which means I can simply click through this. So, grams to moles. Carbon is 12, hydrogen is 1, 3 significant digits, 16.0. Then, guys, we bring moles of our starting point down and moles of our goal on top. Then we need the numbers that balance this, that create the ratio, the stoichiometric ratio. In front of the CH4, there's nothing, so that's an understood 1. In front of the water, there's a 2. And then, guys, finally, we just got to get moles back to grams. So moles of water comes down, 18 grams goes on top. You do the math and you get 39 or 34.9. So, guys, if you were earlier in the day unsure of the questions that you had about mass problems, that's the process. Grams to moles, mole to mole ratio, moles to grams. Do the math, round to significant digits. Go ahead, Sam.
This is just a question about the percent yield.
Yeah.
Like, what if, will we ever have a percent yield from the experiment that is more than the percent theoretical?
That is actually conclusion question number 4 on the lab that we're going to do on Thursday. You want to talk about it for a minute? Let's finish the math and then let's talk about it. Okay? Yeah, go ahead, London. Yeah, so the idea is that the steps always go like this. Oh gosh, hold on. Well, that's okay. We can leave that there. So the steps always go grams to moles. Okay. Then at that point, we go moles to moles, and then the numbers in front of these are the numbers that are in front in the balanced equation. So the 1 and the 2 come from there. And the way that we knew that we needed to go to water is because that is our goal. And so we put water here, and then we do that last conversion to go moles to grams. And it's always those same 3 steps. Was that okay? Okay. So guys, let's then finish the math. Again, we've got some animations. So guys, now we're ready for the last step, which is to figure out the percent yield, and then Sam will talk about your question. So guys, remember we always write down equations before we use them. And no, on the test, me writing down the equation doesn't mean you wrote down the equation, so you're going to rewrite it. So we've got percent yield is actual divided by theoretical. So now, guys, we need some numbers. So you ready? Here we go. Ready? We got 2 animations coming. So guys, what is the actual amount of water that we made? 32.1, so this number comes down. But then, guys, we need to know the theoretical yield. In theory, how much water should we have made? And that would be this number right here. So that number moves down. And then we go 32.1 divided by 34.9 times 100, 3 significant digits, and it's 92.0%. Yeah, and all that does is turns the decimal into a percentage. Go ahead, McKay. No, and you're going to see in lab it gets even messier. But remember, we have a rule, right? It's always the fewest significant digits. No, but what we will do is that when we do the math, we'll always round to the fewest significant digits. Yeah, go ahead. Yep. Correct. Yeah, exactly. Yep. You guys okay on the idea? So guys, what does this mean? Well, fundamentally, this means that of the water we should have collected, we collected 92% of it. So where did the other 8% go? Well, we don't know. But we know that we lost 8% of our product, which is not bad. But Sam, now ask your question again. Right. Yeah, exactly. So is it possible for this number to be bigger than that number? Is it possible to collect more than you should have, thereby having a percent error greater than 100? And the answer is no. Why is it impossible to have greater than 100% yield? There's a law that violates. That's it. You're violating the law of conservation of mass, because if you get higher than 100% yield, it means that you created matter, and you can't do that. So it's impossible to have greater than 100% yield. But Sam, don't stop yet, because here's the deal. Guys, probably half of you in lab on Thursday will have greater than 100% yield. You see the contradiction? Because, guys, we just said it's impossible to have greater than 100% yield because of the law of conservation of mass. But now I'm telling you that's going to happen to you on Thursday. Can you explain it? Take your time. You're fine. What are you thinking? It could be a measurement error. But even if it's not a measurement error, it still is going to happen to a bunch of you. Because what could explain getting greater than 100% error, even if it's not a measurement error? Go ahead, Sam. You started the conversation.
Wouldn't it be because of outside influence?
Exactly. Impurities. There's something else inside your product. The one that you're going to see in the lab that we're doing on Thursday is we're going to carry out a reaction that does make water, but water is not the product that we care about. And what usually happens is your product is still wet. So you're actually weighing water that shouldn't be a part of your product, and it's impurities. So guys, by the way, you're going to see that in the conclusions on the lab. It's going to ask you what explains greater than 100% yield, and the idea is impurities. That's what can cause that. All right, so guys, what else about percent yield? If you're done, I'm done, we're done, and we got one more thing to do in this unit, and then we're done. You done? I'm done. You're done? We're done? Let's be done. Okay, so guys, we are now going to shift gears, and we are now going to talk about what are called limiting reactants. All right. So guys, I don't know why this makes the point so well. I guess I do, because it's fire. All right, here we go. Good heavens. So guys, what I want to do in order to drive home this idea of limiting reactants is I want to carry out a chemical reaction with you. This is not a combustion reaction. The reason this is not a combustion reaction is because the paper in a match is not a hydrocarbon. This is actually cellulose, but it is a chemical reaction. So guys, here's the deal. What I'm going to do is I'm going to light this match, if I could get all this stupid mask stuff off of me. All right, so we light the match, and what is the paper right now reacting with? Oxygen in the air, right? But guys, you'll notice that eventually the flame goes out. It doesn't burn forever, right? Why? Runs out of not just, but which fuel? Ran out of paper. Because guys, if we had run out of oxygen, we'd all be dead, right? We had two reactants. We had paper and we had oxygen. We ran out of paper and the reaction ended. That makes paper the limiting reactant. But guys, you understand in house fires, many times it's the other. That people actually die in house fires sometimes, not because they burn up, but because they suffocate. The fire is consuming so much oxygen that there's very little left to breathe, and people actually suffocate in fires because the oxygen becomes the limiting reactant. Thank goodness that wasn't the case here. Go ahead. Oh, all the time. Single and double displacement. You've got an element in a compound or two compounds. The combustion reaction we just looked at was methane and oxygen. The only time we don't have two reactants is decomposition. Other than that, we've had two or more. Yeah. So guys, you understand just from this silly little thing what limiting reactant means? So here's the question. Why was paper the limiting reactant? Why was paper the limiting reactant? It's really quite simple. Say it again. There's less of it. Guys, we have a whole room full of oxygen and we got a stupid little piece of paper, right? So clearly we're going to run out of paper first. But what if it's not so clear? What if we have a lot of both or a little of both? How will we know which one we run out of first? Well, guys, let's define this and then let's talk about it. So, the limiting reactant is the reactant that is completely consumed in a chemical reaction. In the case of our burning paper, it was clearly the paper and not the oxygen. But guys, the question then becomes, why do we call this the limiting reactant? Well, the answer is because it limits the extent to which the reaction can proceed. So guys, what I want to do, and please don't write any of this down, but I want to, after this, I want to share with you another chemical reaction. And looking at this chemical reaction, we're then going to figure out how to actually figure out which one is the limiting reactant. With a match and a room full of oxygen, it was pretty simple. But what if it's not so clear? You guys all caught up? Guys, after you've written down these 2 thoughts on the board, just settle in. You're going to be done taking notes for a while. Because we're actually going to figure this out. You guys good? You ready to learn about this? So guys, consider if you would, oh sorry, there was one other note. My bad, you should scratch this down. The other reactant, which is not the limiting reactant, is what we call the excess reactant. In the case of in the room, it was the oxygen. This is one of the real drawbacks to my computer not working. I don't have a second monitor that shows me what's coming up next. But again, it's okay. They're going to get me a new one by September. It'll be fine. You hardly even need computers in school, right? It'll be fine. It's fine. It's fine. You guys good? Are you fine? All right. So guys, here we go. Do not write this down, but let me share with you another chemical reaction. And it's this. So guys, looking at this reaction, I've got a question for you. What kind of reaction is this? Single, double, decomposition, synthesis, or combustion? You better be able to answer this, y'all. Single, double, decomposition, synthesis, or combustion? No. It is how do you know it's a synthesis reaction? One product. So guys, anytime you've got one product, you've got a synthesis reaction. And guys, the stoichiometry, again, reviewing things we learned before, the stoichiometry of this reaction is 1 to 2 to 1 to 1. So we've got fluorine, we've got tungsten, we've got sulfur, and we've got bismuth. And maybe you knew that when you react 1 mole of fluorine with 2 moles of tungsten and 1 mole of sulfur, you get 1 mole of bismuth. Yes? No. Guys, what this actually is the recipe for building bicycles. If you take 1 frame, 2 wheels, 1 seat, and bolt them all together, you get a bicycle. We're missing a couple things, but guys, we are going to allow this to be the recipe for building bicycles. So with this said, guys, let me help you through the logic. You ready? Imagine that you decide that you want to get a summer job working like at Mad Dog Cycles. You're the low guy on the totem pole, so they don't let you talk to the public. They don't let you wrench on other people's bikes. They lock you in the back corners of Mad Dog Cycles, and they hand you a wrench, and they hand you a bunch of bicycle parts, and your job is to build the really cheap bikes. But guys, here's the deal. All of these really cheap bikes are actually made of parts that we ship in from China in huge crates. So guys, imagine that they say, yeah, we'd love for you to work at Mad Dog Cycles, and they send you into this dark back room, and there are just these big crates full of bicycle parts. But they're so cheap that you don't buy them by the part, you buy them by the pound. And imagine that you get in there, and there's 120 pounds of bicycle frames, and there's 100 pounds of wheels, and there's 50 pounds of seats. Here's my question. How many bicycles can you build? Or, what information do you need to know in order to answer the question? Go ahead, Rhett. You could, but we're still missing parts. But there is a weight that you need to know. Not how much the whole bike weighs. You need to know the weights of the parts, right? Because guys, it doesn't matter if there's 120 pounds of frames. What you need to know is this. What do they weigh? So guys, imagine that a frame weighs 20 pounds. This is a pretty cheap bike. Frame weighs 20, the wheels weigh 10, and the seats weigh 2. Guys, now, how many bikes can you build? Well, what do we need to do? Well, using this information, we can figure out how many of each part we have. So guys, how many frames do we have? 6. How many wheels? 10. And how many seats? 25. So all we got to do is do the math, and now we know how many of each part we have. Now, guys, how many bikes can we build? Uh-oh. I'm hearing 6 and 5. Why is it 5, Ryan? Because we're not building unicycles. We're building bicycles. And guys, we need 2 wheels for each one of these bicycles. So guys, fundamentally, watch the animation. What we've got to do is we've got to divide by these numbers. And when we divide by these numbers, we get 6 and 5 and 25. And now we know how many bikes we can build. So guys, which of these parts are we going to run out of first? Wheels. So what does that make the frames and the seats? Excess. Do you now understand excess and limiting? Now guys, watch this. Because the same logic that you use to figure this out works in chemistry land too. Look at what we did. So the first thing that we did is we accounted for their mass. We needed to know what they weighed. And then, guys, we needed to account for the stoichiometric ratios because they combine in a 1 to 2 to 1 ratio. Well, guys, chemistry works exactly the same way. The first thing we've got to do is account for mass. How do we do that? By converting to moles. Then, guys, after that, we've got to account for the stoichiometry. How do we do that? We divide by the coefficients. So this then becomes the steps, and I'd encourage you to write them down. Go ahead, Kyle.
How do you separate the product to excess?
Great question. In lab, we're going to boil them off. Yeah, but there's always got to be a way. And actually, that's a brilliant question. So how do you separate from the excess stuff? And there's a whole world of chemistry called separatory chemistry. And it's all about how to get things apart. Sometimes it's precipitation, sometimes it's filtration, sometimes it's boiling. There's all sorts of different ways to. They actually have a thing called a separatory funnel that it's interesting. All right. So guys, step number 1, write a balanced equation. Step number 2, convert mass to moles. Now guys, don't miss the tie back that's in blue. The first thing we're going to do is convert mass to moles. This accounts for the differing masses. Just like we needed to know how much the frames and wheels weigh, guys, here we need to know what the atoms weigh. Convert to moles. Then, guys, step number 3, we're going to divide by the coefficients. This allows us to account for their differing ratios. And then, guys, step number 4, the smallest number is the limiting reactant, like the 5 that we saw with our bicycle building. Did you like the bicycle analogy? I came up with that all on my own. Miss Call doesn't even get credit for that one, which is one of the few things in my life that she doesn't actually deserve credit for. So guys, not surprisingly, what we're going to do now is we're going to do one of these calculations. You will not see this in the lab. In the lab that we're doing Thursday, we're going to make it very clear which one is your limiting reactant, because I'm going to give you a big bottle of it. Or I'm sorry, the excess reactant, because I'm going to give you a big bottle of it. But here, we also need to be able to calculate it. So you all caught up with me? Goes like this. So guys, I don't know if you need to write this down, but here we go. It says 25 grams of hydrochloric acid, 25 grams of zinc. You mix them together, you get the hydrogen gas, you shove the burning splint in there and it blows up, right? You guys have already done this reaction in lab. But when you did it in lab, you just did it because it was fun to blow stuff up. But guys, what if I had given you 25 grams of each and I'd asked you to figure out when's the bubbling going to stop? Which one goes away first? Well, guys, in order to do that, we've got to do the math. So guys, set these up like so. First thing you need is a balanced equation. If you did not turn in your lab because you weren't done, this is number 4, I think. This is the balanced equation for number 4 in the lab. Hydrochloric acid plus zinc makes zinc chloride and hydrogen gas, and then you lit the hydrogen gas on fire. So now, guys, this is going to feel familiar. This is the way to solve these problems. Set them up one beneath the other. Remember when we did that before? Which one was that? Empirical formulas. Guys, this is not an empirical formula calculation. We're going to set them up this way, though, because we are making similar conversions with multiple numbers, and it helps us organize. So, guys, step number 1, convert to moles, like so. So 25 grams of HCl is about 0.7 moles of HCl. 25 grams of zinc is about 0.4 moles of zinc. So clearly we have less zinc than we do HCl, in the same way that we had fewer frames than we did wheels. It's the exact same math. What does a frame weigh? Divide how much you've got by the weight of each frame. What does an HCl weigh? Divide the amount you've got by how much each one weighs. But guys, in the same way that when you did this with the bicycle parts, you had to account for the fact that you needed 2 wheels for every frame. Guys, here we need 2 HCl's for every zinc. So we've got to account for that by dividing by the coefficients. So we divide the HCl by 2, we divide the zinc by 1. In the same way that we divided the wheels by 2 and the frames and the seats by 1. Now, guys, the smallest number is your limiting reactant. At that point, the smallest number becomes your limiting reactant. But guys, understand, you need to then communicate which one that is. So which is smaller, top or bottom? Top or bottom, which is smaller? Top. That's your limiting reactant. So you just need to write down a simple 5-word sentence that simply says, this is the limiting reactant. And then you're done. So guys, that's it. Questions on limiting reactant calcs? You guys are good? Okay, so in front of you, you have, holy buckets, is it 20 minutes? 20, this is the old one, right? That was our assembly schedule. Can you guys believe we had an assembly last week? It sounds weird, but it was almost like emotional. Like, oh my gosh, we are all together. That felt good. So, guys, you now have 25 minutes. This is the last homework assignment of the unit. It is assignment number 4. Please notice, guys, that it is 2 pages. On the first page, I did not give you enough room to work. On the second page, I did. And guys, the next 25 minutes are yours. Dig in, spend your time well, ask questions as you need. Don't forget to turn in your homework tonight, the stoichiometry assignment. Go get them.